welcome to the 7th lecture in the series on sequences of functions. This is likely to be the last lecture in the series. What we plan to do in this session is to give a more technical version of a result which you had already seen. You may recall we proved if Fn is a sequence of continuously differentiable functions on a bounded interval AB, and if Fn converges uniformly to F and Fn dash converges to G uniformly, naturally G is continuous, then we said F is differentiable and F dash equal to G. And it will be worthwhile to go through just within 20 seconds. You can go through the proof used to fundamental theorem of calculus. You wrote Fn of x equal to some Fn of some point plus integral a to x Fn dash of t dt, right? And you use uniform continuities to show that Fn dash, the integral a to x Fn dash t dt converges to integral a to x g of t dt, etc. Then by used fundamental theorem of calculus to show that F dash equal to G. Please go through this kind of proof. Just because you have gone through the proof, understood, you should see how simple the proof is. So next, we had also seen a result where the following was proved as an application of the Cauchy criterion for uniform convergence. What are the result? You have Fn is a sequence again on a bounded interval such that for some point C, Fn C, the sequence of real numbers converges, and Fn are differentiable and Fn dash converges to G uniformly. Then using the Cauchy criterion, we proved the Fn's themselves are uniformly convergent. Please go through the proof. That's what we did in the last 6th lecture, right? Now what we want to do today. Let us get started. Since I want to finish this within about 35-40 minutes, I think it may be better that I get started. So let us do that. What the result we want to prove is the following. J is a bounded interval, and Fn's are differentiable functions, and there exists some point, call it A in J, so that Fn A converges, the sequence Fn A converges, and these are the assumptions. And 2, Fn dash converge uniformly to some G on J. Then we want to conclude Fn is uniformly convergent on J, 1, and 2, and 2, let us say to a function, of course a continuous function F from J to R. Then what you want to conclude is F is differentiable and F dash equal to G. Is the statement clear? Notice this hypothesis is exactly the same hypothesis which we used in the last result in the last lecture. From that we using that we concluded 1. So 1 was already concluded, was already done, where as an application of Cauchy criterion. It's a very interesting proof. Please go through. This kind of proof you should just try to go through 2 or 3 times so that you will see the fear of whether you will remember will go away, because you would understood so thoroughly the same way now you remember your multiplication table, right? You memorized it when you are in primary school. Now all of a sudden you can say, if I ask you what is 7 times 7, or if I ask you what is 8 times 9, you know that. Why? The practice. The same way you have to review. Good. So that is done. What all we have to prove is F is differentiable and F dash equal to G, right? We need to only to prove 2. This is all I have to do. Good. So I will take a digression, because in my series on differentiation on or in my book, Okay, I had given a very powerful characterization of differentiability of a function in terms of something to do with continuity. Because this is my practice, those of you who had been seeing my videos or read my book, you will know I follow the mathematician's trick. What is that? If you have some new problem, you reduce it to, oh my gosh, yeah, I'm sorry, the screen was not shared as usual. So I hope, let's quickly go through. J is a bound interval, f(n)s are differential functions. There is a point A such that f and A converges, and second, f(n) dash converges to G uniformly on J. Then the first thing we want to conclude is f(n) is uniformly convergent on J to a continuous function. Naturally it will be continuous because f(n) themselves are continuous, and if f(n) converges uniformly to f, then f has to be continuous. This one we had already proved as an application of Cauchy criterion in the last lecture. Okay, please go through the proof. And therefore I need only to prove f is differentiable and f dash equal to G. Is that clear to all? Good. Okay, now what I claim is that in my book as well as in my videos on the series of differentiation on R, I have stated and proved an important characterization of differentiability of functions, which makes life easy. Many of the standard algebra of differential functions can be very easily reduced to the algebra of continuous functions. The same way in continuity I reduce it to the algebra of convergent sequences. Okay, those of you who have read my book or my videos will know these things. Okay, right. So the same way I want to, and I do not know how many of you have gone through, and if I ask you now to go through, you may not even do that. Yeah, how many of you will do? You may not. You know differentiation, why I necessarily go through it. Yeah, very good. So I'll take about 5 minutes to quickly recall that. Okay, suppose f is a function from J to R and A is a point in J. I want to say f is differentiable at A. This is the theorem. Okay, if and only if, okay, there exists a function G such that two things happen. F of x equal to f of A into g of x into x minus A for all x in G, and 2, G is continuous at A. You understand? Okay. And suppose this happens, then you may ask, okay, if such a G exists, you may ask, then f is differentiable, therefore what is f dash A? Okay, if such an f exists, such a G exists, then f is differentiable by the theorem, therefore f dash at A is G at A. Okay, please spend some time, understand this statement. If you had already seen, you can go faster. Okay, now let's go through the proof. Assume f is differentiability, right? Okay, now what do I know? I want to find such a function G. Let's look at one. For x not equal to A, I can solve for gx. Do you see that? If x is not equal to A, then I can solve for gx. Gx is nothing other than f of x minus f of A by x minus A, if x is not equal to A. Do you see that? From 1. No, I remember I have to prove the existence of G. If such a G exists, it has to satisfy 1. If it satisfies 1, then I can solve for G. You see that I am working backwards as usual. You understand? But remember, I am supposed to show, I have to make sure that G is defined at each and every point. So I have to tell you what is G at A. Right? Now let's look at, you say that G is continuous at A. Right? Since G is supposed to be continuous at A, right? Therefore, limit G, what should be GA? GA should be limit x tends to A of gx. But what is gx? That is limit x tends to A of fx minus fa by x minus A. But what is our assumption? F is differentiable at A. Therefore, if limit x tends to A of this difference quotient will be f dash A. Right? So This motivates me that I should define as f dash a. You understand this? This is just a motivation. Okay, I am working backwards. Now you can ignore. Okay, assume f is differentiable at a. Okay, define. Now, okay, define gx equal to fx minus fa by x minus a for x in a, j, and x not equal to a, and equal to f dash a if x equal to a. You understand? Right? Then obviously g satisfies 1 and 2. Right? Cross multiply, you get 1. Right? And what is it? Its value at a? It's f dash a. And just because limit x tends to a of gx equal to f dash a, therefore g is also continuous. Do you understand this? Sure? Okay. So we have proved if f is differentiable, okay, such a g exists satisfying condition 1 and 2. And what is g at a? By very construction is f dash a. You understand that? Correct? So the last conclusion is also true. And how many of you are confident that you can go through the converse? Suppose such a g exists, okay, with satisfying 1 and 2. Right? Okay, then what is that I have to prove? I have to prove f is differentiable at a and f dash a is ga. This is what I have to prove. Yeah, good. What is f dash a? That is limit x tends to a of fx minus fa by x minus a exists. This is what I have to prove. Right? But remember, what is fx? G exists, therefore fx is fa plus gx into x minus a for every x in a, for every x in j. Therefore gx is going to be fx minus fa. Therefore this is same as, this object is same as limit x tends to a of gx. You understand this? This difference quotient is same as this. But what g satisfies 2. That is g is continuous at a. Therefore limit x tends to a of this will be g of a. You follow that? Therefore what I have shown, the limit fx minus fa by x minus a as x tends to a exists and it is equal to ga. That means f is differentiable and its derivative at a and its derivative at a is ga. Is that okay? Please quickly revise. If you have not seen this earlier, this is the first time, please go through it. Okay, this is a very beautiful characterization. Okay, you may wonder why I need this. Without this characterization I may be able to complete the proof, but this characterization will motivate why the proof starts with something very strange. Yeah, let us go. So I am going to prove this theorem. So one is already proved, therefore I am going to assume my f1 is uniformly convergent to f. F is given, also now known to me, namely limit of f of x equal to limit of f and x. Is that clear? Okay, so I am not going to repeat anymore. Is that all right? Okay. So we start with the proof. Okay, we know what we know. There exists a continuous function f from j to r so that f1 converges to f uniformly. In particular, for each x in j, f and x converges to fx because pointwise convergence was assumed. Is that clear? Now what is that I have to prove? I have to prove f is differentiable. Okay, and also I have to say something. Okay, that is f dash equal to g. What is g? It is the uniform limit of g, f dash, f and dash. These are the things I have to prove. Yeah. So what we are going to do is fix any point c in the interval j. Right. Let us look at gn of x. Now you will see gn of x, how I define it is the so-called auxiliary function which I define. Okay, let me call this function, the function g, as auxiliary function. Okay, so what I am going to do is I am construct f's are differentiable, therefore I know the auxiliary function gn exists and f and dash c if x equal to c. Is that okay? So what do we know about Gn? We know the Gns are continuous. They are continuous everywhere on J. Do you understand that? Why they are continuous on J? Because let's look at. Okay. What do I know about fn of x? They are all continuous functions, and fn c is constant. Therefore, this is a continuous function. All right. For x not equal to c, and for x not equal to c, x minus c is non-zero. It's a continuous function. Therefore, 1 upon x minus c is a continuous function at x not equal to c. Therefore, the product fn of x minus fn of c by x minus c is continuous at x not equal to c. You understand that? Therefore, Gn is continuous at x not equal to c. But Gn is continuous at x equal to c also because of the construction. Do you understand that? Therefore, Gn is continuous on all of j. Please pause, review, proceed. Right, now we want to claim, okay, Gn is uniformly convergent on J. To show Gn is uniformly convergent on J, what is the trick? Now that you have gone through the last video, you should know. I have to prove Un is uniformly Cauchy. And remember, uniformly Cauchy you had already seen something similar. You have done that. You understand this? Do you remember in the last lecture on uniform Cauchy, when I wanted to apply to prove this version 1, the first conclusion? Where is that? Yeah, this first conclusion. Fn's are uniformly convergent. Okay, we went through this kind of argument. Don't get confused. Always go back and forth, so that you will know you are confident. Okay, mathematics and no thinking is linear. Unfortunately, textbooks and teachers come prepared and give a linear thing. You think that's the only way to do. That is easier for you to understand. Okay, check logically it's correct, but it may not allow you to think on your own. Okay, anyway, I keep talking about such things. Anyway, so what is that I have to prove? I have to prove Gn is uniformly Cauchy on J. Right? So what does that mean? That I have to show for each x in J, I have to find a uniform estimate, Gnx minus Gmx. I have to estimate uniform. Okay, uniform estimate for this. Yeah, okay. So let us look at that. What is Gnx minus Gmx? This is fnx minus fnc by x minus c minus fmx minus fmc by x minus c. So what do you think I will do? I will have x minus c common. But if you remember last lecture, you would remember I will not write fnx minus fnc minus fmx plus fmc. I will not write. What will I do? I will club fnx and fmf together. That is, I will write as fn minus fm of x minus fn minus fm of c. You understand this? Do you remember this is what we did in the last lecture? Right. Now call this as a function something like phi. Of course, this phi depends upon n and m also, but let's not worry about this. Therefore, this is phi of x minus phi of c. Is phi differentiable? Yes, because fn and fm are differentiable. Therefore, their difference being phi will be differentiable. Therefore, it's phi x minus phi c by x minus c. So what do we know? By mean value theorem, I know there exists a xi between, may call it a t, it will be easier for me to, t between x and c. Okay, I don't know which is x, which is t, but there will be t in between, right? Therefore, I can write it as the derivative fn minus fm dash at t into x minus c by x minus c. You follow that? Yeah, right. Now remember, this t will depend upon what? X, c, m and n, because the function phi depends upon all these things. Okay, phi depends upon m and n, and mean value theorem that t depends upon x and c. Therefore, my t depends upon x, c, m and n. Okay, you should always think of such things. Just like that, don't write. Okay, now what is it I wanted to estimate? So this cancels. So I wanted to estimate gn of x minus gm of x, that is equal to fn dash of t minus fm dash of t. You understand this? And t is what? I do not want t's. Yeah, but then you remember, what do I know about fn dash? This is uniformly Cauchy, right? Therefore, if you give an epsilon positive, I know there is an n. Okay, so that for all m and n greater than or equal to n, and for all t in the interval j, uniformly Cauchy on j. Okay, what happens? fn dash of t minus fm dash of t will be less than epsilon. You understand that? Therefore, for any n and m greater than or equal to n, this will be less than epsilon. Therefore, gn, this is true for every x and g also. Yeah, right? It is independent of x. I got it. Yeah, so gn is uniformly Cauchy on g. Therefore, gn converges to uniformly to a function g, and g is continuous on g. Because gn's are differentiable, continuous we already observed. Sorry, gn's are differentiable, not sorry, gn's are continuous, not differentiable. Remember, we already said gn's are continuous everywhere. Is that all right? Okay, good. So gn's, are you happy now? Okay. Now what is that I want to prove? Okay, now I want to prove f is differentiable at a. What is a? Not a, c, yeah, at c. C is some arbitrary point of j, right? So if I want to prove this is differentiable at this, what should I do? I should do, I have to prove fx minus fc by x minus c limit exists. Or I have to prove fx equal to fc plus some function, call it xi of x into x minus c, where xi is continuous at c, right? This should be true for all x, that is xi satisfies 1 and 2 of my characterization. Do you understand? Yeah, right. Now how do I get it? Now what is fx? Fx is limit of f and x. What is fc? It is limit of f and c, right? I do not know what is ix, but x minus c, right? Can I write something here? These are the limits, right? This converges to this converges to this, and this is okay. Something converges to this, but let me not worry about. Do I get this? Now let's look at what is g and x. G and x is f and x minus f and c by x minus c. Therefore, fn of x is going to be f and c plus g and x into x minus c. Do you understand this? Yeah, therefore what should I write here? G and x. Okay, I'm as usual working backwards, please don't get confused. Okay, if I write a textbook proof, I will start with observe this. From this, observe this, take limit. Okay, then what do I get? As n goes to infinity, I will get fx equal, f and x will converge to fx, f and c will converge to fc, and g and x values it converges to? It converges to gx, right? And x minus c will be x minus c. Is that clear? This is point wise now. For each x, this is true. Yeah? Therefore, what I have shown? I have shown that fx is of the form f of c plus g of x into x minus c. This is true for all x and j. And is g continuous at c? Yes, because g is uniform limit of gn. Gn's are continuous on j. Therefore, capital G is also continuous on all of j, and in particular is continuous at c. You follow that? Right. Now, what can you conclude? Do you remember my characterization of differentiability? By that characterization, I know f is differentiable. Where? At x equal to c. So we proved one part. What is that we have proved? F is differentiable at c. What is c? C is an arbitrary point of the interval j. So we have proved it. Yeah. In case you may be curious, where do I use j is bounded? That's because when I wanted to conclude one, that is fn's are uniformly convergent, okay, we used uniform Cauchy criterion for that. At that point I had something like mod x minus c, that is less than or equal to mod b minus c. Okay, so I wanted the boundedness there, okay, just for fun. Okay, I always go back and forth like that so that I feel confident in what I am using. Anyway, and many of you may get confused, may be disoriented, but don't worry, just go back and understand. Okay, when you read a book now you will see the proof will be very crystal clear. Very good. Okay, now G is continuous, sorry, differentiable at C. Therefore what should be f dash of C? By my characterization it must be G of C. But what am I supposed to prove? Go back to the definition. I wanted to prove f dash of x equal to G of x. That is f dash of C must be little g of C, whereas what I got is capital G of C. So what is that I have to prove? I have to prove capital G of C is nothing other than small g of C. Yeah, let us do that. What is capital G of C? Capital G of C is limit over n of Gn of C, right? But what is our Gn of C? Remember, it is fn dash of C. Yeah, what is Gn of C? Gns are the auxiliary functions, right? Yeah, yeah, fn dash of C. Is that clear? Yeah, therefore G of C is this, right? Very good. This is fn dash of C. Now let's look at fn dash of C. Therefore G of C is limit fn dash of C. But remember, what do I know about fn dash? It converges uniformly to G. In particular, it converges pointwise. Therefore fn dash of C, where should it converge to? It should converge to G of C. Right? Uniform convergence implies pointwise convergence. Therefore this also should be equal to G of C. By the uniqueness of the limit, I know capital G of C is nothing other than small g of C. Do you follow that? Therefore f dash of C equal to G of C. So pause, review, proceed. So we have proved the result completely. Okay, right. So more or less all the theory portions are over. Just I want to look at only two examples, because in this kind of thing the teachers are always fond of the so-called counter examples. Okay, so let us look at what we have proved. We have proved if fn's are differentiable and fn dash converges uniformly and also fn converges uniformly, I can also assume that G, then we proved f dash equal to G, right? This is in some sense, what does it say? Limit fn dash, take it this, whether it's equal to limit of fn dash. You understand that? Because what is f? Limit of fn, its dash is this. Okay, this is this object and this is this object, because fn dash converges to G. You understand that? So what does it mean? A limit and differentiation, they are commute, right? You take the limit and then differentiate, or you take the differentiation first and then take the limit. Okay, whether the results are the same. Under the assumptions of the theorem, the results are the same. In general, that may not be true. So usually teachers will talk about a counter example. Okay, okay. In general, this may not happen. This may not happen in general. Yeah. So let us look at a so-called counter example. Let us define f1 of x equal to x power n by n on the interval 0, 1. Right? And then f1 converges to 0 pointwise. That's very easy for you to prove that. Okay, because you already know x power n converges to 0 on the interval 0 to 1 pointwise, and fn of 1 will be 1 by n, that also goes to 0. Therefore this goes to 0 pointwise on J on the interval 0, 1. Is that okay? Now what is fn dash? That is x power n minus 1. right? Therefore, what is the limit over n of fn dash of 1? Remember, fn dash of 1 is just 1. Therefore, the fn dash of 1 limit will be 1, right? But what is your limit function f? That is, what is the limit fn, and then take dash, that is 0 function, and take its derivative, that is 0. Therefore, these two are not equal. Are you following? This is not equal to 0, which is limit fn and then take dash. Limit fn is 0 function, and its derivatives, it's a constant function, therefore its derivative is 0. You understand? Therefore, at 1 it's not true. In fact, I have to look at only at 1. Okay, are you following? Okay. And similarly, there is a second example, something to the integration. Do you remember we proved integral a to b, a limit of fn equal to integral limit of fn a to b. That is, if fn converges uniformly to f on closed and bound integral a b, okay, f is integrable, and then a to b fn converges to integral a to b f. Okay, in classical language they will always write like this. What is that? You are first integrating and then taking limit, whereas here you are taking the limit and then integrating, whether they are equal, whether these two operations, in some sense, you know, all of you know algebra, right? Whether they commute. Okay, limiting operation and integration, do they commute? What we proved is under uniform convergence, that's a true statement. In general, it may not be true. Okay, this example also I will be very brief. Okay, so what do I do is by means of so-called tent functions. Okay, let us look at something like 2 by n, where n is very large. Okay, a natural number, very large, right? Let us say make it greater than or equal to 2 or something. Then let's look at 1 by n, right? The tent is, it's a tent function. Okay, the pitches are here, and then it peaks out at here. Okay, and peaks out at n. Okay, this will be when n will be very large. So I may not be able to draw a correct picture, but I hope all of you will understand. Okay, so this, and then it vanishes here. Okay, and after that it remains 0 here. Yeah, do you follow that? The height is here n. Oh, the height is here n, y equal to n, right? Yeah, so if you remove, so this is my graph of the function fn. You can easily write down very good expression, because remember 0 to at 1 upon n, at 0 it is 0, at 1 upon n it is, therefore this point is 1 by n comma n. This point is 0 0. This is a line segment, so you know how to write down the equation of the line. That is the definition of fn on the interval 0 to 1 by n, and 1 by n here it has to come to 2 by n. This point will be 2 by n comma 0. Therefore you again write down the equation of line joining the points 1 by n to 2 by n 0. That will be the equation of the, that will be the expression for the function fn on the interval 1 by n to 2 by n. After that it is 0 function. Fn will be 0 for x greater than or equal to 2 by n. You understand? This is a very trivial 12th standard exercise. I don't want to spend time. Okay, now I want to know what is integral of fn between 0 to 1. Again, if you remember, integral is the area under the graph for a positive function. Okay, therefore the area is going to be the area of this triangle. But this area of the triangle is very easy to compute, right? This is the area of the, twice the area of this triangle. This triangle has base 1 by n, height n by n, and therefore half bh. But then there are two such rectangles, therefore 2 times 2. Two such triangles, therefore it is 1. Therefore integral of fn is always 1. Do you understand that? But what is fn? Limit fn of x. Okay, fix x in 0 1. I want to know what is the point use limit. Okay, That's again easy. It's very easy to look at. Suppose this is my thing, my x, right? I only have to choose an n so that 2 by n is less than x. You understand that? Can I do that? By Archimedean property, I can always do that. Therefore, what will be if n is such that 2 by n is less than x, then what will be fn of x? Because my x is to the right of 2 by n, therefore it will always 0. Therefore, for any x, fn x is eventually 0, eventually constant, namely constant 0. Therefore, what is the limit? Limit of n, fn x will be 0. Right? Therefore, what is the limit function? Identically 0 function. What is the integral? It is 0. But integral of fn is always 1. Therefore, limit as in integral of fn 0 to 1, this will be 1. But integral of limit fn 0 to 1 will be 0 to 1, which will be 0. So they are not equal. Yeah. So I think all of us got salvation with these counter examples. I hope all of you enjoyed this series of lectures. Please go through. As usual, I think aloud, I go back and forth. Okay, and it may be a little confusing if this is the first time you are watching my videos, but if you had watched some of my videos, by now you know how to think. It will be easier. Okay, after that you can read any one of your standard textbooks like my book, or Bottle and Sherbert, or Rudin, or Apostle, or Ross Analysis Theory of Calculus. These are all excellent books. Any one of the books you can read, you will see the proofs are crystal clear to you. Okay, some of the subtle points which they may not explain had been done here. And if you wondered why the proof worked, how did anybody thought of such a proof, you know this. That is my main purpose, so that in future you will be able to think on your own. If there is a problem, you should be able to think of what is the question I should ask, how to look for a solution. Okay, that is more important training. Okay, not line by line checking. That's a verification. Yeah, I hope all of you enjoyed. Stay tuned. Okay, we will come up with the next series. Yeah, stay safe, take care.